yellow team, and our presentation concerns the pressure control lab, and it will be covering the steady state operating curve and the step response. Okay, start off my presentation. I'll go over the background theory behind it, explaining the system schematic and the information flow into and out of the system. Then I'll go into the steady state operating curve, and then I'll show you how we acquired our data, and show you how we organize our charts. And after that, I'll get into the step function, where I'll describe the transfer function, and I'll show you the data we acquired for the step up and step down functions. Okay, so this right here is our system schematic. This is a microscale version of a paint booth in a motor assembly plant.
Can you do that again?
Huh?
Can you do that again?
Do what?
Take it forward.
I guess. Here we go. Click on it, and it blows up.
Sweet. Sweet. I think he gets extra points for that. Maybe even a clap. Suppose that will happen again during this presentation?
I'll save the surprise. Okay, like I said, this is a microscale version of a paint booth in a motor assembly plant in Dunlap, Tennessee.
By the way, that plant's closed now.
Oh, is it? The plant's closed now. But this system is a user-controlled system. It works via the internet. You enter inputs into a web-based program. It sends the data here to this pressure record control. This is what controls the system. This device is located on the control board. From here, this sends the information to a pressure control actuator, which actually controls a variable speed blower. The variable speed blower blows air into these three booths. Depending on how the dampers are set, the increased pressure boost forces air out the filters. That cleans the air for them. You have a pressure transmitter, which records the data coming into this, sends it back to the pressure recording control, which creates a feedback loop for the system. Okay, this right here is a schematic or a diagram showing the information flow into and out of the system. MT is a manipulated variable. That's what we input into the system, which basically is a percent power for our blower. Goes in the system, comes out as a control variable, which basically regulates the booth pressure in the system. Okay. Data collection for our steady state operating curve. We designated each experiment for 20 seconds at 10% intervals. We ran each experiment with damper 1 closed, damper 2 open. For our step response, our experiment time was 30 seconds. We did a 10% step increase at 10 seconds. We did this for each 10% intervals. And again, we also ran these experiments with damper 1 closed and damper 2 open. This is an example graph for how we obtained our steady state operating curve. This is a pressure output, 50% power input. As you can see, it goes up and kind of levels off right there, about 15 centimeters per water. We only collected data from this section right here where it's stable. We ignored all this because this isn't a system in steady state. So we use graphs like the, do that. We use these data to obtain graphs like this. We found our operating range of our steady state operating curve between 10% and 100%. As you can see, the results were fairly linear. This was done with only one trial, so we didn't average results. So if we were to average results, I would expect that we'd see even more linear results. The error bars here represent our standard deviation, which gives us a 95% confidence level. So you can see our operating range is there. Okay, for our step response, this is the goal. We were trying to get a transfer function for our step response, where gain is equal to the change in output or the change in input. Our time response, of course, is approximately 63.2% of the change in output. You take that output, and at the time that occurs, that's your time constant. Dead time is the time at which the system starts to change. Here's a graph for our system. Our change, this is for the step response at 60%. We did input change at motor power 30%. Our change in output was about 10 centimeters water. Okay, calculating our 63.2% of that gave us about 24 centimeters of water. After subtracting from this, I didn't show this in the graph because my graph was getting really busy. So we calculated time constant to be about 0.26 seconds, and our initial time, or dead time, was 10.17 seconds, or 0.17 seconds after the step occurred. Okay, so we roll this in, we come up with our transfer equation. This right here is in the Laplace domain. These are all our values. Okay, we did the same thing for the step decrease, where we stepped down 30% in motor power. The change again was I forgot that. That's supposed to be 10 centimeters of water. I'm sorry. But we put all that in. On this one, our time constant was 0.19 seconds, and our dead time was 10.1 seconds, or 0.1 seconds after the start of the step. Plug all this in. Here I got the revised data, but give us this, and this again is in our Laplace domain. I charted the step up and step down gain value, and right here the lower values was at 20% power, the mid values was at 50% power, and the upper values was 80% power. As you can see there, they're not too far associated with the standard deviations. They all sort of fall in range with each other. The outlier here is this upper value. It seems like the gain value actually decreases a little bit as you get towards the upper values. Let's see. Move that up here a little bit. And conclusion is our operating range, like I said, was between 10 and 90% for our steady state operating curve, which is pretty much what the customer wants. It shows that we can consistently operate within those results. Our step response, our step up and step down were fairly similar as far as gain time constant goes. The only outlier, of course, was on the upper values, where it seems the changes that seems to diminish a little bit. Any questions?